Okay, welcome back.
Hello again.
Hey, how's it going? Let me see here.
I left to use the bathroom. What is the problem?
Oh, I just I couldn't share the screen for a second. Let me just put it here in notability. Okay. And then I go Zoom, admit more people. And okay, share content, share screen. Start broadcast. Okay. Hopefully, let me know if it falls apart again. Oh no. Okay. So I was just going over the fact that there's another way to calculate variance, which is just to take the expected value of the square of the random variable and subtract off the square of the expected value. So if you do this together, if you do this, you get the variance formula continuing from over here. This would get us to, this would be equal to 81 over 6 minus 3.5 squared. Okay. Any questions on how to find the expected value and variance for a discrete random variable? All right. So I'm going to show something that if you've seen a little bit of calculus, or and you don't actually really even need to know calculus, but the idea is nice. So this table where we multiply x times p of x and we add them together, I told you that kind of like represents sort of like a histogram. And if you're thinking about what this looks like, you can think of this. It's sort of like, let me think here. It's sort of like the weighted average. X is like your position on the x-axis. Then p of x is like the percentage. So it's like your weighted position. So you can do this with a continuous random variable. I'll just write the formulas down. It's not, if after you take calculus, you'll learn more about it. But if you have a continuous random variable, the formulas are completely analogous. But rather than use the summation sign, and this is a common theme in math, rather than use a summation sign, we're going to use an integral sign to represent the area. So what you do is, if you have a continuous random variable, the expected value of xi is going to be equal to the area underneath the curve of the distribution times x dx. This is like you have your distribution curve, you multiply it times x, and you figure out the area underneath that. And the idea is that there's this thing in calculus that whenever you want to try to find the area under a curve, you can use something called the integral. If this is f of x, and you find you're interested in finding the area underneath the curve, we write this is an infinite sum kind of little pieces f of x dx. where dx is like a little thing like this. So you see, if you one way to think about this is like you're adding up a bunch of little rectangles, where f is the height and dx is the width. And yeah, so this is kind of, yeah, this is what you would do for a continuous random variable. There's a connection between this formula and the regular expected value. Rather than summing the numbers, just the discrete things, you're going to be integrating over a continuous range, and you're finding like the area under this curve.
It could just be because I'm not that well versed in calculus, but wouldn't that integral just always be 1?
Good question. So what you're thinking about, and this is the key idea, you're thinking about this formula, which is correct. And here we usually, when we write where we're integrating from and to, we write like this. So this tells us to integrate over the entire number line. What you're thinking about is this one. You're completely right that the integral of the probability curve is 1. The integral of the entire density is 1. But what we're doing is, just like for expected value, we are multiplying the density at a point times the actual position of the point. And what we're getting there is really just a weighted average of our position. You actually do this calculation in physics. Have you guys ever seen that eagle that will like balance on your fingertip no matter how you kind of tilt it? Or sometimes it's like some sort of bird, just like a statue thing that does that. Have any of you guys ever seen that?
I have seen the funny bird.
Yeah. So that, do you know why that one like kind of doesn't tip over that much?
I do not.
So the idea is that it's perfectly the center of mass in all like x, y, and z positions, or rather x and y, is set up so that its center of mass is right at the beak. And if the center of mass is wherever the center of mass is of an object, if you try to balance it there, it's going to be very stable. And so if you have a distribution that looks like, that looks like something, a small weight over here, maybe it could be like a distribution with 2 bumps. Where would you think, and maybe it doesn't go on forever. Maybe it stops like right here. It could go on forever potentially, but it has to overall add up to 1. If this was like a, let's say, this represented like a piece of wood, and you're looking at it from the side, where do you think it would be a balancing point for the wood along the x-axis?
I would think it would be like somewhere just a little to the left of the top of the big hump.
Exactly, somewhere like right here. And so that's what this is showing, is that so this point would represent the expected value. That's all expected value is. It's really the weighted average of your position values. And in physics, it gives you the center of mass. Okay, and then there is a formula. I'm just going to write it down. It's completely analogous to the one for discrete ones, but instead of a sigma, we use the integral. So the variance of xi is going to be the integral of x minus mu squared times p of x dx. So rather than adding these quantities, we are integrating the density times the x minus mu. So okay, so this I don't want to get too far off here, but this is just like the fact that if you have a discrete variable or a random variable or a continuous variable, there's ways to calculate its expected value and ways to find its variance. Now let's go back to the central limit theorem. Let me copy and paste it. And so, yeah, Quinn, with all of the problems with the normal distribution, I never actually asked you to calculate the standard deviation. I always just gave it to you, because technically to calculate it from some distribution, you'd either have to do if it's a discrete one, you'd have to put it in Google Sheets, or otherwise you'd have to do some integral. But luckily, we don't have to worry about that. But we will again be estimating sigma using the data points. Okay, so what does this say? If you have repeated things, then regardless of how xi is distributed, the sample mean which we call x bar, it's equal to x1 plus x2 all the way to xn all over n. The sample mean is a random variable that looks a lot like a bell curve. With with the expected value of x bar
Chester's in the waiting room. He got kicked.
Okay. Thank you. Okay, so that looks a lot like a bell curve. The expected value of x bar is equal to mu, and I'll go in depth here. And the variance of x bar is equal to sigma squared, or sorry, sigma squared all over n. So let's think about what this is saying. Do you guys agree that if I draw, like imagine I have like a lottery picking machine, or a lottery like with the Powerball or whatever, where the balls come out through the vacuum or something, and then you get the lottery number. Imagine I have some distribution of numbers, and I draw a ping pong ball one at a time from that machine. And then every time I draw one, I put it back and I do it again. Do you guys agree that after I do this 100 times and I take the average, that I'm not going to get the same number every single time that I do that? Is that a reasonable statement?
Yes, sir.
Or maybe like maybe yeah. But what's your intuition tell you? Like, let's say the balls were numbered 1 through 100 and consecutive numbers. So every number from 1 to 100 is likely. What do you expect the average to come out to be looking like? or let's say 0 to 100. If you, yeah, maybe 0 to 100. But I don't know.
50.
It would look like 50, right? Because everybody, is close. 50 is in the middle of everything. So, but Quentin, would you expect to get exactly 50 if you picked 100 balls? Would you expect the average, and each of them is randomly drawn independently? Would you expect the average to be exactly 50?
I would not.
Right. Could it be like 51 or maybe 50.8 or something like that? What do you think? Would it be weird if it was 90?
That would be a tad bit strange.
Right? That would mean like somehow you picked 100 numbers. Oh, sorry. You picked yeah, well, I said, okay, so you're picking out of 100 balls, but you're also picking it many times. Somehow you picked a bunch of numbers that are all close to make your average like 90. If you pick one ball or two balls and you got like 70 and then you got 83 or something like that, that wouldn't be too unusual, right?
Yeah.
But if you did it with like 100 or 1,000 times and you got an average that's way above 50, you'd be a little suspicious. So that's what this is saying. That's kind of the gist of this statement, is that so x bar is a random variable. That's a really important thing to be aware of, because it's a sum of, it's the average of other random variables, so therefore it must be random itself. But the average of the random variable of the average of the sample mean is mu. The expected value, because we expect each of them to be mu, so if we add them all together and divide by n, you can figure out that the expected value of the mean is also mu. But the interesting thing is that the variance is getting smaller. And that's not so surprising, because as you take more and more items, we expect that the distribution of the average value, it's random, but it gets tighter and tighter, or closer and closer to the actual expected value of the original distribution. And the central theorem is this part that, the central limit thing is the part that says it looks a lot like a bell curve. Regardless of what you start with, after you do this, as you take larger and larger samples, the distribution of the sample mean starts looking like a bell curve. So we've actually already seen an example of this, and it's one of the nicest examples, but we didn't really talk about it as interpreted that way. So let's say you have a really simple success, failure, or 0, 1, 0, 1, or another term is Bernoulli, for these two brothers who were really into probability in, I think, the 1700s, well, maybe earlier, I'm not sure. I have to look that up. But there were these two brothers that were really into gambling and probability. They were mathematicians. So simple failure 0, 1, Bernoulli probability.
Just so you know, we can't see your screen right now.
Oh no! How long has that been?
5 minutes.
Oh really? Okay. Thanks for letting me know. Let me see.
Yeah.
Is it going to happen again? Let's see. Start broadcast. I don't know why the iPad is. Oh, maybe it's because my battery is really low. No, I'm okay on the battery. Can you see now?
Yeah.
Okay. So this is the statement. So if you take the sum of a bunch of random variables, divide by n, and you call it the sample mean, that's its own random variable, and it turns out it's going to look a lot like a bell curve. And this is a difficult statement to prove, but it's just a mathematical theorem, and you can observe it happening a lot in nature. And we get the expected value as mu, and the variance of this bell curve is getting smaller and smaller. So here's an example, and we'll just draw a few little instances of this. So let's say we have a Bernoulli probability of flipping a coin. So Bernoulli is chance of success is 1, and chance of failure is 0. And this is P 1 minus P. These are the, this is a really simple success failure. If you repeat this over and over, you end up with the binomial distribution. So let's see here. Yeah, so let's say that we have, let me think here. Okay, yeah, let's do it this way. So let's say it's 50-50. So let's say, just to make it simpler, let's say P equals 1/2. So this is just like flipping a coin 0 or 1. So if you repeat this over and over, every time you flip a heads, let's say you add 1, you get plus 1, and every time you get tails, you get 0. So basically, you're just getting a bit of, you're getting either a 0 or 1 with chance 50-50. So let's say we have a random variable x1, x2, x3, x4, and x5. By the way, what is the expected value of this random variable?
0.5.
Nice, 1/2, because it's 0 plus 1 over 2, so it's just 1/2. You can do this more generally if it was if the probability was just p, it would be equal to 1 times p plus 0 times 1 minus p, so it would just be equal to p. Okay. Now let's say we do the sample mean with 5 draws. So we do sample mean equals x1 plus x2 plus x3 plus x4 plus x5, all over 5. Well, what are the possible outcomes here? Is it possible for the sample mean to become 0?
Yes.
What's the chance of that happening?
You would need, so it'd be 1/2 to the power of 5.
Perfect. So the chance, if we start to plot the distribution of x bar, the original distribution is like, the original one is 0, 1, and it's like 50-50. This is 1/2, 1/2. But now we have some slightly different situation. So the chance of getting a 0 is 1 out of 32. So 1 out of 32. And that's similarly the chance of observing getting exactly 1. This is also going to be 1 out of 32. What's the chance of getting x bar equal to 1/5?
Is it 5? 5 out of 32? Sorry.
Perfect, exactly. Probably x bar is equal to 1/5. So let's put 1/5. So these are the possible values. It could be 1/5, 2/5, 3/5. 2/5, yeah, 2/5, 3/5, 4/5, and 5/5. So just one. So X bar, if you flip a coin 5 times and you count how many heads there are, right? You can get any number from 0 to 5, and we can calculate the probability. It'll be 5 out of 32. This one would also be 5 out of 32 because it's, remember, 5 choose 1. And what about, what's the middle number? What's how many ways are there to get 2 heads out of 5 flips?
10.
Nice, because it's 5 choose 2. So this would be 1032, which is about a third. Okay. So this doesn't really look super like a bell curve, but the idea is if you were to do 50 draws, and of course it's not a continuous distribution. You can't get like, for example, you can never get, because it's an odd number of zeros and ones, you can never get 2.5 over 5. So that wouldn't make sense. But that's not what we're talking about when we mention the central limit theorem. We say that the distribution, as you increase n, it starts to look a lot like, or almost indistinguishable from a bell curve. So let's see, if we do 50, I'm not going to write out the probabilities, but I'll do the outcomes here. So it'll be 1 over 50, 2 over 50, and so forth, all the way to 49 over 50. But most likely, you're going to be around 25 over 50. And the shape that you observe will be like some sort of a bell curve, like that. But it's going to be bars, right? It's going to be like little bars, and you know, you guys know, like 1/2 to the 50th power, like to get something out here is going to be like like it's something I heard, like 2 to the 50th, or maybe 2 to the 100th is like it's a really, really big number, maybe even more than like particles in the universe or something like that. I'm not sure if that's true, but it's very big. So it's very unlikely to observe if you're doing 50 flips to get 50 tails in a row. Okay. And so that's the amazing thing, is that we see if we draw for something repeatedly, we don't need to have prior knowledge about what the original distribution looks like to make a probabilistic statement about the distribution of the sample average. That's the key insight of the central limit theorem. And can you guys see it? Are there any questions about this picture? So let me show you, let me go to a website that I really like, and I'll share this as well. Seeing theory. So this is one of the best websites. It's really cool. Like I'm just with my finger now, and I'm like, yeah, I think this is awesome how they designed this. So let's see, let's start it. So yeah, these are some cool things to explore, like variance here. We saw this formula earlier. If you draw a card, let's see here. If you draw a deck from 10 cards, you get the average of the square differences. So this is looking at the sample average, the sample variance versus the true variance of the distribution. So if you do it 100 times, they're basically saying that the green square starts to look a lot like the blue square. That's what's happening there. But that's not what I wanted to show you. Compound probability, probability distributions, central limit theorem. Okay, so what we're going to do here, can you guys, can everyone see this okay?
Yeah, I can see it.
Okay. So the top curve, we can use these numbers alpha and beta to basically make a bunch of shapes like that have area underneath the curve. So therefore, they're all valid probability distributions. This is kind of cool. It's kind of like a flubber or something like that. Yeah, it's like, it looks like it's almost alive. So these are all just random. This is just the probability distribution. And in fact, if you saw in the beginning, I think I could make a, well, this is like a weird one. Where was it? I saw one, I could kind of look kind of like a triangle. So, you know, this sort of looks like a triangle. So where do you guys expect, if I pick a random number from this distribution, where do you expect it to fall on the line? Like how far along the line? At the beginning, on the left side or the right side?
Like a fifth away from the end of the right.
Exactly. That's where most of the distribution is located. So you know, if we draw one, if we take a sample of size 1 and we do it one time, it's going to fall right there. But now let's just increase our sample size. So it's like we're picking marbles out of this kind of blob. Let's do it 9 times. So 9 balls dropped, and then we calculate the average. And then it's the bottom line represents, like, it's going to represent a histogram of how many times we observed a certain sample average. So far, so good. Any questions about this picture? So let's do it 2 times. So we're going to repeat the experiment. We're going to draw. We're going to sample 9 times from the triangle and take the average, and we're going to repeat this experiment 2 times. Well, maybe I should have restarted it, but whatever. Did everyone follow what happened there? Anyone have any questions about that picture?
That's 3 draws, right? Because it kept your old one, and that's why it's...
Yeah, it kept the old one. That's right, exactly. Otherwise, it would be 50-50. So let's do some more. Let's do it 10 times. And so it's going to be 9 dots, like it's like raining 9 dots. And then each time it rains 9 dots, we take the average position of those and we just put it down and we mark where that came out. And we're going to keep a histogram on the bottom. Okay, that doesn't look that interesting. I mean, kind of has an interesting shape, a little bit like a bell curve, but not quite yet. So not quite yet. So let's just kind of make draw more and more. Okay. So we get this. And so this is a lot like when we were talking about with the flipping the coins. You can only get certain outcomes, or your outcomes might not look exactly like a bell curve if your sample size is not very large. But if we increase our sample size now, and 15 is pretty large. I mean, 9 was pretty large also. And we keep doing this. And we keep doing it again. And keep doing this. I think it takes a little while. unfortunately, I can't do the. Oh, you know what? Maybe I should have done. So unfortunately, the buckets on this bell curve are not very. The buckets are not set up really nice. But if you had smaller buckets, you would start to see the bell curve shape look really, really clear. Maybe if I do something like this, and I draw it out, and you keep doing it. And also, the sample size here is, it doesn't let me get it to a really large sample size. So the sample size of, even though I'm doing lots of draws, as I do more and more draws, it's only going to approach the probabilities of a size 15 sample. But let me think, does that, yeah, it might not look exactly like a bell curve until I increase the sample size even further. But that's the idea. Regardless of what you pick, what shape you pick in the beginning, you can, you're going to get some sort of bell curve. Like if you do this crazy shape and you keep doing keep sampling, at first it doesn't look like a bell curve. Maybe it doesn't even ever, but it will start to look like a bell curve if you had the bins set up correctly and you took a large enough sample size. And it's a bell curve all the way pushed to the right. But when it gets skinny enough, it'll, you can kind of imagine the part to the right. Let's see if we can do the theoretical. Yeah. So it'll start to look like that. That's the idea. Okay. What do you guys think? And do you have any questions about this visualization? So next time we will continue, and I'll post some con stuff that we'll be due next week. But we're going to now apply this idea to be able to talk about the distribution of things that we don't know how to distribute it. But if we want to understand what's the average distributed like, and what's the chance that the average is located in some interval. And we're going to be able to do that because of the central limit theorem. And that's really, the central limit theorem really underpins the ability of like a forecaster to say, hey, I think there's a chance of the average of, of average height to be in this range, even though maybe I don't know how height, or maybe like the average preference to be in this range, but maybe they don't know the actual distribution of preferences or stuff like that. Okay, I will see you guys next time. Are there any questions? Oh, let me see if there's any comment here. Okay, cool. Yeah, and mess around with that. I'll post a link to that site. I really like it. I'm always happy to talk about that. If you notice anything cool or curious about something there, just let me know and we can talk about it in class, because I think they did such a great job. And the first few topics are like things that we did like with conditional probability and expected value and stuff. So you should have the tools to mess around and understand and interpret what they designed. All right, guys, have a wonderful rest of your day. A great weekend.
Thank you, Daniel.
Thank you, Daniel.
Daniel.
Thank you.
Thank you.
So,
Hey,
if you
yes.
change the page source, you can alter the like limits that it puts in place.
Oh, really?
Yeah. Do you know how to like inspect element?
Yes, but I don't know if I can do it on my iPad, but
I don't think you can do it on an iPad, not that I know of. Yeah, but if you the limits are just written right into the HTML, so you can alter them.
Oh.
You can't change the
Can-
size of the bars though.
can you share your screen? Oh, you can just
Oh.
oh, I see, I see.
Yeah.
Oh, so I can change the number of draws.
Yeah. So like you see, I have the sample size all the way up to 100 here, whereas you could only get it up to like 15.
Oh, that's cool. That's really cool.
Yeah, I can't change the width of the rectangles though because they're pre-constructed.
Oh, I see. What about his link? I think that link might have a better visualization of the
This guy?
yeah. I'm not sure if it's still active. Oh yeah, okay.
Yeah,
Yeah.
file not found.
Blocks.org. Yeah.
It's a shame.
There's a few interesting like videos. I'll try to find them where people they drop balls from it's like a pinball type of thing, like steel balls, and there's like nails, and then it just has to drop like randomly each way, and then at the end, if you drop like 1,000 of them or 100, it starts to form the bell curve also.
Oh, Plinko boards?
Yeah, that's right. Yeah,
Yeah.
exactly.
I like those.
That's it. That's what we learned today.
Okay, thank you, Daniel.
Okay, see you, Quentin.